Good afternoon, this is Schweitzer, and this is the start of our first little section on motion, rotational motion. And this particular video is going to be focusing on rotating around a circle. Okay, so one of the things you're going to find right away is this idea of a radian. And a radian is something that I think tends to scare kids. Because it's mostly because they don't really know what it is. Um, it just sounds foreign to them. So I would say that if you're in that boat, really a radian is the same as a degree. That's not the exact same measurement. It's like this is like feet and this is meters. So 360 degrees gets you around a circle, and so does radians. Okay, radians get you around a circle. So how many radians does it take to get you completely around a circle? This 2 pi. Now again, this might be the part where starting to cause people a little bit, students a little bit of nervousness. Like, why is this pi thing? What does this mean? So it's just a number, really, right? We know that pi is like 3.1, so it's really 2 times 3.1. So to get around a circle is about 6.2 radians. And again, if you don't understand or have knowledge of how a radian gets its value, that's okay, because you probably don't know why a degree gets its value. Why is it 360 degrees all the way around? Why is it 180 degrees to get, halfway across? You have no idea, and to be honest with you, I don't either. But a radian, as we post a little video here, it's got a little bit of a geometrical little relationship between um, what a radian is, and that's fine too. But ultimately, we're really looking at here. Okay, just it's a means of flipping around a circle, and you should be realizing that to get once around a circle is 2 pi. That's an important value to kind of keep in your mind. Okay. Now, most people, most students, you give them a second or two, or give them a phone, internet, and they would be able to come up with the fact that the circumference of a circle to get around is equal to 2 pi 2 pi times the radius. Okay. So often we use this formula, but instead of using 2 pi, this is the radians around the circle. We often can use the symbol theta to represent that as well. So I could take the 2 pi out and say, okay, theta is going to be my radians around the circle times r. And now this is a much more useful formula because I can put in whatever radians I want, okay? And then 2 pi times r would give me the full length of the circle. But if I want to get halfway around the circle, well then if the whole thing is 2 pi, then to get halfway is just pi. So if you put pi in here, you're going to get half the circumference for half of the circle. Okay. So this is a pretty fundamental formula that I use to derive lots of stuff that we're going to be using. Okay. So keep in mind this formula, and I'll be 100% honest with you in the sense that these formulas that we'll be using aren't things that people use every day, and it takes a little while. It took me a while to get them into my working memory, so I have to think about them every single time. And if you're feeling frustrated that you don't feel like you know this stuff very well, it just takes a little bit of work. And you shouldn't pretend that you're going to be able to memorize everything immediately. You got to simply derive it from this formula right here, for example. Okay. So don't memorize things. If you're going to memorize something, memorize that. Circumference circle is 2 pi r, or circumference circle is theta r. That's really the only thing that I really would memorize. Everything else works right off of that. All right, so next up here, it says, what is the relationship between radians and degrees? Okay, so we have a couple things that we use somewhat frequently be radians, which is a rotation, obviously, degrees, which is a rotation, obviously, and we also have a thing called a revolution. Okay, so going around. So a wheel has undergone 100 revolutions. Okay, so 1 revolution is equal to 360 degrees, which is equal to 2 pi. This is just a linear relationship between these things. So our whole idea of factor label is all we need. And we're just going to use these linear relationships. We could use a proportion if you'd like. But a wheel undergoes 100 revolutions. How many degrees is it rotated? Okay. So in this case, I just say 100 revolutions, revs, dot line, get rid of revs, and go to degrees. And 360 degrees is 1 revolution. There you go. So take a moment. That's 360 times 100. All right. Tack on 2 zeros. We got 36,000. Now, how many radians has the wheel rotated? Well, it's simple enough too. 100 revolutions. Get rid of the revolutions and go to radians. Well, 1 revolution is just 2 pi radians, and therefore you could multiply it out. It would be 200 pi. 200 pi. This would give you the exact value. You could substitute the pi in if you'd like to get a decimal value. How far did the wheel travel during this revolution? Okay, so in this sense, we need to use this guy right here. So the circumference, or the actual uh, linear distance around the circle, okay, is what we're asking for here, is going to be S is the distance here, R pi. So it's going to be, the distance would simply be R and then 200, slowing down here, pi. If you give me R, I will give you the length of the actual distance here. So it depends at this point on how big your wheel is. If a small wheel rotates, 100 times versus a large wheel rotating 100 times, it is a lot different. Okay. In fact, quite often you'd have, this would be a pretty common example of an old-time bicycle, right? And I don't know, I'm not drawing a very good one, but this person would have a really big front wheel, be probably more like right here, and they would have a little pedal here, crank here, and that was a pretty common bicycle, right? Didn't make many revolutions here. 1 revolution here in this small circle made a large rotation here, and therefore lots of distance. Whereas this back wheel spinning around real fast. All interesting physics. All right. So now, what is angular velocity? Oh, that just sounds complicated, right? So really, velocity. Let's think about this. This is going to be your, in the linear sense. Linear sense is going to be the change in distance. Okay, divided by the change in time. So this is going to be, angular velocity is symbolized by a little W-looking thing. Um, and it is going to be the change in angle, change in theta, divided by change in time. Okay, there you go. That's it. We call this angular velocity. Units typically for us would be in radians per time, and second is a pretty common time. So a radian per second would be a pretty common time. And this is something that, again, I'm not going to memorize any formulas. I guess I memorized this one, okay? If I want to know what angular velocity is, I just go back and think about it. It's change in angle over change in time. And I got that from here. I didn't memorize what this was. If I forget what it is, I just rederive it again. All right, what's tangential velocity? Now again, this is a situation where we could have 2 wheels, one big, one small, okay? And let's say this guy is 5R and this guy is R, okay? And let's say they're traveling at the same, rotating at the same rate, okay? This guy makes a rotation, this guy makes a rotation. But you would notice that at this point, this one here is, even though they're spinning the same rate, this one is traveling a larger distance, okay? This guy travels, let's say, a quarter of a rotation. It travels this distance. This one travels a quarter. Look at the length of that line. Okay, so the tangential velocity is the actual velocity of the distance. If you were an ant on this wheel here, okay, how far did you travel as it rotated through? Okay. All right. So now let's figure that out. I don't want to memorize anything here. So the distance around the circle was S, they sometimes call it. That's an older term. Just call it S. It's fine. And 2 pi r is the whole way around. 2 pi r. So that's the one formula that I want to kind of memorize, you might say. But 2 pi r is the whole way around. Okay. So let's just say distance equals the amount of theta that you go around times r. So this is the actual distance that you're going to travel. Okay. I don't know how far much the wheel rotated around. Okay. We could say it traveled one time around. That's fine. Now again, so this is the actual distance. Now keep in mind, distance divided by time. And all I gotta do is divide by time. Okay. So with this, we call this velocity tangential is just equal to the amount of theta times r divided by time. Now, at this point, again, I didn't memorize anything. All I did was I had to work my way through it, and you should be comfortable that with this little formula and this idea and understanding what it is, you should be able to derive that. Now, one last thing we'll mention here, okay, is that what we got here? Notice that we have angular velocity is angle per time, and we have that right here, these two. So velocity tangential is also equal to the angular velocity, how fast you're turning around per time, times r, the radius. So this guy here has 5 times the angular velocity than this guy does. There's no squares or anything like that here. So you should note that this guy's velocity tangential is 5 times this guy's velocity tangential. Okay. So in one rotation here, if you're an ant or you're zipping around on a bug on the wheel, it goes one time around, and the same amount of time it goes one time around this guy has actually traveled 5 times farther than this one, okay, in that amount of time. Okay. So the velocity tangential is 5 times. All right. So all right. All right. So again, angular velocity. All right. This little W-looking thing is often referred to as omega. Okay. So, and what units to have? Let's review here. Omega is radians per second. A penny sits on a rotating disc and spinning at 1 revolution every 2 seconds. Convert the rotation to radians per second. Now, a radian per second would be an angular velocity. Okay, so 1 rotation in every 2 seconds. So I need to have my angle per time. So 1 rotation is pretty straightforward. That's just 1 time around the circle, whichever way you want to go. That's just 2 pi. And we're doing that in 2 seconds. So 2 divided by 2, and my angular velocity is just pi radians per second. Okay. So speed, now the speed at which it moves, okay, is, we call this velocity tangential, okay. I just derived this earlier, radians turning times r divided by t, which would be this, so the speed that this thing actually moves, okay, around, would be that of a angular velocity times r. Okay. So a little bit of an application there. All right, so frequency and period. Okay, so what is period? So period is if you have a circle, let's say that penny or that um, bug on a wheel. So the period would be the time for one revolution. Okay. We often symbolize it with a capital T. Okay. So in this case, what's frequency? Frequency is going to be the number of revolutions per just 1 second. So in this case, typically a frequency would be something, a unit might be cycles per second. And a typical unit of that is a hertz. And a typical, another way you might see it is 1 over s, something happening per time, and or you might just see it as s negative 1. Okay. Now this guy is literally a time. So its unit is going to be just a time, and that's it. A couple things you should note about this is that the period is equal to 1 over the frequency, or the frequency is equal to 1 over the period. That's all pretty important stuff here. Okay, so period here, do your units work? Okay, so again, period is the um, time for one rotation, and we have the speed here, we have rotation, and everything cancels out, and it would just be time. Okay, so let's look what we got here. It says if a rope swings around and has a period of 2 seconds, what's the frequency? Okay, so in this case, the frequency is just 1 over 2, or 0.5 rotations per second. And we'll just do per second. And you could do, let's say, revs per second, revolutions per second. Because if it takes 2 seconds to get round, okay, then, so the rope swings has a period of 2 seconds, so that means in 1 second, it only gets halfway around. And that's where this guy's coming from. What's the angular velocity? So let's rehash what angular velocity is again. It's the change in angle per change in time. Do we have that? Okay. In this situation,
oh my gosh, I'm sorry.
So in this situation, we have what do we have for our period, our angle? To rope to swing around in a frequency is going to be so it swings once around in 2 seconds. So we're going around. How far we go around? We go 2 pi around. That's once around. And we do it in 2 seconds. And therefore, once again, our angular velocity is pi radians per second. Okay. Find the average angular velocity of a softball pitcher's arm in range seconds if the ball, if in throwing the ball, her arm rotates 1/3 of the revolution around in 0.1 seconds. Okay. So in this case, let's try it out. You should be able to try it on your own. This is a good example, so always pausing it here. I have a revolutions per second. This would be 1/3 over 0.1. And this would give you a unit of revs per second, which is something that we might use. Your car rotates its motor, and they use revolutions per minute. But I just need to convert this guy over to radians, and then I would be in my unit that I want. So let's just take this thing and convert revolutions to minutes. 1/3 revs, get rid of revs, and go to radians. What's my relationships here again? Well, 1 revolution is 2 pi. Okay, and I'm going to grab my calculator and just do this. So I'm going to take 2 pi divided by 3. That's kind of 2 pi divided by 3 equals, so 2/3 pi. So I'll do 2 times pi divided by 3. And I'm going to get 2.09, and that's radians. And remember, keep in mind, again, I know this is all new, but to get all the way around a circle is about 6.2 radians. So this individual's just barely making it around two of these guys. All right, divided by 0.1 seconds, and we're going to get divided by 0.1. That's pretty easy math here. 20.9 equals 20.9 radians per second, and that is my angular velocity. We'll end there for today. Thank you very much.